Hey, welcome back. I am gonna check something on the stream, make sure we are good to go. So, close out some of this stuff. All right, got that. Coming in here and view the channel. Hey, welcome back. I am gonna check something on the stream, make sure we are good to go. So okay, so this seems to be working. I'm gonna mute it and then go over here. And let's see what happens if I switch to different scene. And it looks like I gotta slow this down. So I should be able to switch back and forth between my coding and my writing, and we'll give it a shot. So right now we're in the writing, and yeah, so we're down here. So we were talking about some creating differential equations to solve problems. So there's this general kind of method called that variational calculus. It's a really powerful set of tools where we can find like minimum of functions of function and those kind of things. And we use that to come up with the Lagrange equations that d dt dl d. I'm gonna write it. Let's leave it as like v and x minus dl dx equals 0. It doesn't have to be v and x. Like in general, the way that it's kind of written, it's like a q dot and a q, where q could be x. It could be like an x1, x2, x3. It could be a whole bunch of different parameters. It could be a theta. It could be anything like that. And then q dot would be like a v1, a v2, the change in all those parameters, v3, anything like that. And then I did some math. I was kind of doing things, and if you go through some extra work, you can get to this cycloid differential equation. I guess it is ordinary, but cycloid differential equation, where we say y prime squared is c minus y over y, or you could call this like c over y minus 1, something like that, where the derivative squared equals constant times that function itself. And I think in that first video we were using like f of x, so maybe we would write this as like f prime f and f and f, where we've got this. And this parameter c, come up here. If we look up that cycloid ODE, you can come down here. And I know it's kind of weird to like use Wikipedia for math solutions, but rather than get like bogged down in all of the magic of kind of going through this, we can get to like this idea that the diameter over y minus 1 is our differential equation. All right, so I'm bringing that up because I want to, so I have f prime squared equals d over f minus 1, something like that. This is my differential equation that I'm trying to deal with. We'll come back up here, come back to scene 2. And so I grabbed some of the code from this like varying paths. Main thing that I wanted was this function, this f and then this t thing. Like if I know what that f of x function is, then I should be able to find like some minimum t value in here. But I have this new function in here called ordinary differential equation, and let's come in here and let's say my cycloid, I want to create a function. Let's zoom in some, right? Function of cycloid ODE. Input is going to be f. And then the and let's add another term here, like diameter. So I'll say fp squared equals d over f minus 1, and then return fp squared, fp2 to the 0.5, and we'll end it there. Let's see if that gives us, so we'll say cycloid ODE, we'll just say the current function is 0.5, diameter, we'll give it a diameter of 1, and just want to figure out, is it giving me something? Cycloid ODE, I swear I did fix it. Did I mess up the values here? And I'm just double checking stream, making sure that, all right, good. So we got everything. You can see the same errors that I'm getting. What is the problem here? We can ask AI. Oh, I don't love that. Oh, X, duh. I'm using Python. And let's do a dot just in case we have, and a dot right here. Okay, so if I run this and I say it's 1/2, then it's 1 over 1/2 minus 1, and I get a 1. So if I give it a value of function and I give it that diameter, then it'll give me some result. And for this ordinary differential equation, I want to figure out like how to use this to actually integrate something. So let's look it up. Julia, well, do we want to use AI? Start jumping into AI? We can try it. Ask AI. Show me an example of using show me an example of I see. swear this was... I kind of like this better anyway. Just looking at the docs already. Okay. So if you have a function, you need it to be u, p, and t. What is the p for? So let's just try, at least try like this code, so we can see how this thing works. So I want to start this with a begin, and then at the end of this cell, say end. Oh, yeah, I don't want to import plots again. And let's take a look at what this thing is doing. I like to put things on multiple lines when I can. And this is all just documentation, so I didn't actually use AI in this. So solution is solving this thing where ODE problem is defining this function with an initial value and a time span. So then it's plugging that into the solver, so this ODE problem solver, giving it some inputs about like what kind of method it's using. Let's see. And I think it would work even if all we said was solve prob. Maybe it would look a little different because it's a different solver, but for the most part, it does give us an answer. So TSIT 5, it's just TSIT 5 is Satora, so a 4-5 Runga-Kutta method. And that's fine, we could use that. So let's take this, see how we can plug it into our problem for this cycloid ODE. We want, rather than a t-span, we want an x-span. A u0 is the initial value. So we'll grab all this. Begin. End, and we're going to call this f of x, p, and t. I'll leave that parameter p, but I'm going to plug this in. Cycloid ODE of well, this should be an f of x, right? So it should just be returning one derivative. So this function should give us one derivative. So let's just try it. Cycloid ODE of f and 1. Give it a. And then our initial height is 1. Or sorry, our initial value should be 0. Give that a shot. And we'll call this like our x span because we're going to go from 0 to 1. Oh, f of 0 should be 1, right? Let's call that f0. Should be 1, and we're going to go from 0 to 1. And change this to X span. So what I'm doing here is kind of changing the idea of this ODE instead of like a time varying. I just want it to be an X varying. The fact that I labeled it X versus T doesn't really matter, but and then up here this F of F, I don't love. It's a dummy variable. So really I'd prefer to call it DF, but the fact that I'm saying F of F, it doesn't really matter. But really the cycloid ODE, the main thing that I want it to do is that if I give it a function, if I give it a function value, it's going to give me the derivative at that function value. And that way I can integrate over space. Really, ODEs are usually over time, but space is fine too. And then let's plot that solution. Really all I need is this, right? Oh, multiple SOLs. Let's just comment out this whole thing. It doesn't like whenever you use the same variables in two spots. Should I delete this whole thing? Now it's commented. Should be fine. Didn't like this, so it starts at 1 and slope is always 0, so it never changes. Interesting problem. Not a very interesting problem, but it's not exactly what I was going for, right? What if this is like 2? Is it still the same thing? Oh, probably a divide by 0, or, yeah. Okay. Leave that as 1. So I'm getting some imaginary values. So let's go back to drawing board, figure out what I'm doing wrong. So I have this differential equation. It's supposed to define like, nope. As I'm kind of rolling this way, this is the path. That's the path of like this point as this thing kind of rolls around and rolls forward. And this whole function this is my f of x. And it should be, the way that this should work is that f prime squared is always equal to d over f minus 1. So f of 0 should be equal to d. So d over d, f prime squared is 1, is 0. So that's why it's not changing at all. So what if we started at like 0.1 and then call this like d times 0.99, then at least we would have something we would have something non-zero. So we could try that. So let's try 0.01, call that 0.99, go from 0 to 1. Oh, it still doesn't like that. So what is 1 over 0.99 minus 1? What? Yeah, so what's wrong with that? I don't know what the problem is with that. It might be coming to the point where domain error, 10 to the negative 7. So it's saying that it's a complex result. It might not matter. So what I was trying to show is like how to use this ODE problem solver in Julia. I'm having a little bit of trouble. That's okay. That's all part of the learning process, right? We'll figure it out. And maybe this is just a weird problem to solve with differential equations. That could be it. Let's back up. So yeah, we'll come back to our other. So if we come down here, say f prime squared equals c minus f over f. So f prime squared times f equals c minus f, and then so plus f equals c. One thing I could do is just take a derivative, get rid of that constant, right? So now this whole thing is equal to 0. Then I end up with an f double prime. So 2 times f double prime times f prime times f. I think I did that right. Plus f prime to the third. And then plus f prime is all equal to 0. Then I could solve for f double prime instead of f prime. And I think I'm doing this right. You never know, right? Get rid of this one. So So then one of these f primes goes away, up here and up here. So now I have an f double prime is this 1 plus f prime squared. I guess, do I still need that idea that f of 0 is still going to be 1, because I'm still trying to say that I want to start at 0 and 1 and go to 1 and 0. So I'm still trying to figure out what is this path. The variational calculus got us to this answer, but now we got to use something to solve that differential equation. This is one way, is that you have a differential equation, just brute force, say, computer, solve this for me. You run into different issues, like we're running into here, where we have these problems with like complex numbers and stuff, but we can try it. All right, so let's come back to Julia in here. So let's do this cycloid ODE of, I'll call it U now instead. So it's going to give me, let's look at the live docs again, because what I want to do is find, in here, Lagrange of du, function Lagrange of du, u comma p comma t. This is what I want, of like, here I've got multiple inputs. This one's, here's a second order differential equation, which is what we have. Get this a little bigger, zoom in some. Lagrange, all right, so here we've got dv, v, u, p, and t. Oh my god. This is different than what I'm used to, but that's okay. We'll figure it out. So u of 1 is dv of 1. So dv, v, u, p, t. And I've used these ODEs before, but I've been doing SciPy integration for so long, now I'm forgetting like what these parameters are. So let's try this. dv, v, u, p, t, where dv is our output, so that function is describing our output. So function cycloid ODE, we want df f I'm just copying this in. So we want a df and f, x, no, a u, let's call it a ddf, a df, and an f, and then a p, x. So this, parameter. So omega is that parameter there, and that's fine. So we want to say cycloid ODE. And let's get rid of this one. Delete. inputs are DDF and we don't need D anymore because we're changing this one to let's go here. Because I know I grabbed this harmonic oscillator, and this is what I was using before. DDU, DU, U, omega, and T. And then DDU is omega squared times U. And that's it. Second order ODE. And that's what we have here. Cycloid is a DDF, a DF, and an F with a and then I'm going to say DDF equals 1 plus DF to the second. Let's do a dot just in case. Gives a few things, divide by 2, and divide by F. And I think that's all I need, right? And then return a DDF. Hopefully this is beneficial to kind of see somebody. I like to do it live so that you can see, like, it's not always just a straightforward, like, one and done sort of thing. Even I mean, we can plug this into AI and try to get some help, but I wanted to try it my own way. Everything is going to be okay. All right, great. And now I don't even need this thing. I'm just going to call this cycloid ODE. I guess the thing that I don't know is what the slope is at 0. Because really, if it's a second order differential equation, you need 2 initial conditions. Yeah. Negative 100. Should be a steep-ish. Or no. 0? 0? I don't know. I don't know what the... Let's go back to this one. So how did I plug in? So I have a dx0 and an x0. T-span and omega. So start with a df0, then plug in the f0, and then give it x-span. And so these big error, I don't love the big long errors like this. Like it is giving me the final thing, like what the problem is. Oh, prob. Yeah, problem is this. But that can't be the issue, this line. It's got to be something before that, and it's up here somewhere. And let's make sure this thing is giving us what we want. Yeah, how are you supposed to check dot equal? Maybe I should have a dot equal there. Materialize. All right, going with AI. Let's see what the problem is. I am running the Julia ODE problem solver. I think that's what it's called. Or no, this one. Solver, but getting an error with my ODE function. And actually, should I grab this one? Is this where I'm trying to run the solver? Let's give it this thing. I'll just tell it that I'm getting an error and see if it can help me figure out how to troubleshoot this function. Because this one's a little weird to me that I need to give it the DDF but then also return the DDF, but I don't know. ODE. Yeah, I know that they work on first order systems. All right, so we could try it this way. A du, a p, and an x, and then I like this approach of saying like, hey, I have two inputs. Yeah, and I guess the p is just a parameter in here, right? So let's grab this. And this one doesn't have that DDU, right? Yeah, now I'm surrounded by error messages, right? This exclamation point, I wonder, yeah, what does that? Oh, set global once? Contour, no. And then, don't I need to say return? I guess it'll just, that is my output. Oh, the output is du. The inputs are u, p, and x. Don't I need a dot? I guess not. Cycloid ODE. It's not defined, but I'm defining it right here. So that means there's something wrong with this, even though it says that it's running. I'm going to get rid of this one, so it gets rid of that cell. Why do I need that? So now I think I would say a U0. So now it's going up instead of down, but that's okay. We'll figure that out. And then U2, this must be the derivative in here. I want to know what's in that solution. So there's a sol.t. So this is really like our x values. Oh yeah, this I can put back to 0. Is it u? So sol.t is a vector, sol.u is that, I just want one of the things. Just so that's the very first data point. So colon, comma, 1? No. 1, comma, colon. Huh. How do I get just one value? Because here I'm plotting both of them too. Because I just grabbed SOL. Yeah, I'm just plotting like the function. Plot just the f of x function. All right, so I have to 1, comma, colon. That's what I tried to do, right? Oh, 1 bracket colon, not dot. No dot. Ah, there we go. Weird. So 1, comma, colon, like that. And it goes from 0 up to 2000. Can't be right. And the slope is not negative 100, right? from 0 to 1. So I'm trying to figure out how, or I guess here it's going 1 to 1.25, describing this curve here. Really I want it to go down, so I could just plug in a negative like that, but it should be the opposite curve, like coming down first. This is kind of describing the opposite motion, like going up, and it's not reaching the bottom like I want it to. So really this is turning into like a shooting method too, which is another form of like differential equation solving, where we have to define a function where this initial value is a parameter, and we're going to keep changing it until we hit the right 0 at the end. But I don't want that to be negative. So u0, let's say 20. So it's sloping up, negative 20, sloping down, negative 100. It's weird that it swings back up so quickly. Can I grab the last value? END. So the last value is this 81. What I'm gonna do is grab this, so I have that problem as this one. Oh, I see. So I need to define it like this. And really, what I want to do is like minus 0 of like creating a 0, because I want it to be 0, but that's okay. I can just call it like that. So now if I say my shooting of 20, I get 121. If I say 10, it's 36, 5. So I'm changing the initial velocity, trying to match the end result of 0. So now let's pull in here of what is a root finding method in Julia, because that's what I want. What I just did was defined a problem where if I know the right velocity, it'll equal 0. And using roots and secant method, I just want a default one, so let's just Google it. Nonlinear root solving. It is a nonlinear problem. Standard interval. We can try this one. I'm just going to grab this code and see if it works. All right. So because we're in Pluto, it wants a begin and end, and it doesn't like these initial conditions. Let's call it x0, x, x, x. Oh, and it doesn't like SOL. Problem, solution. Oh yeah. So it gave me something. 1.4. Let's see what we get here. Yep, 1.4, 1.4. So it is working. But now my problem is called my shooting. X0, we can call it, we'll say 10. We don't need a parameter P. We'll just call this an X0 like that. Oh, didn't like that. I thought I grabbed it fine. All right, come back to Copilot. And plug this in. I'm working on a shooting method to solve for the initial slope df dx for my ODE. I defined the my shooting function that needs to be solved with nls.solve. Why am I getting an error? And I'm not even giving it what the error message is. It might have something to do with, like, maybe I need to bound the problem or something, but we'll see if this one helps at all. Because this is telling me that there's something wrong maybe with parameters or something, but that doesn't really make sense because I'm just plugging in a like a D, really it should be like a df, right? Dummy variable. this one. ODE blow up. It could be an ODE blow up, something like that. Since I have that 1/2f, not a bad guess. So maybe add something. Minus target. Yeah, my target is 0. Comma target. Okay. Oh, is it using Newton's method? I mean, it's using nonlinear problem solver. Disable. Solve. Broyden. So I could use a Broyden. So I could try this. Wasn't that all part of one auto diff no add? Like that. Still doesn't like that though. So let's give it the error. Here is the error. Oh, and this video is getting a little long. Probably want to watch some of this in fast speed. Wrong signature. What's going on? Problem requires this or that, but we had neither. G or that. So I could include this into my function. But it doesn't like that one. It's weird. Huh. It didn't like that. Okay. So let's change this back. Maybe du is not defined. Can I just say du is 0, 0? And then rewrite it. Or can I say that it's a df in this? So the main thing that I was doing here was just, there's something, I'll have to look into that exclamation point because it's a little different from what I'm used to for differential equations. I'm sure it's a pretty powerful method. It seems like it's worth figuring out what it is, but I just changed it so that I'm just specifying the output the way that I'm kind of used to it. But now I'm still running up against this issue where Newton-Raphson, I don't think this is going to solve it though. Okay, yep. All right, so I'll come back to this, try again tomorrow, and we'll see where we go from there. All right, I won't keep everybody too long, but I'll play around with it, figure it out, and then we'll jump back, try again. Okay, thanks for joining.